It's my great pleasure to introduce Professor Charles Isbell. He's a professor in the School of Interactive Computing and the Executive Associate Dean at in the College of Computing at Georgia Institute of Technology. His lab focuses on applying statistical machine learning to building autonomous agents that must live and interact with large numbers of other intelligent agents, some of whom may be human. So he and I know each other from a long time back. We were both at AT&T Shannon Labs back at the turn of the millennium, which sounds like a long time ago. And he led a project there that was really way ahead of its time on Cobot, a social reinforcement learning agent, a chatbot that existed in a rich environment called LambdaMoo. So as a friend of Charles introducing the speakers, I have sort of one of two possible strategies. I could try to tell a story from back in the old days and embarrass him. Unfortunately, Charles doesn't embarrass. There's nothing I could possibly say that would embarrass him. So the other thing I could do is set an impossibly high bar with incredible praise about the great talks he gives. So I'll just say that he gives super entertaining talks, sometimes that are quite wacky and non-traditional, and that he never disappoints.
So thank you, Peter, very much for setting me up for failure. I appreciate that. So good morning, everyone. Good morning, everyone.
Good morning.
All right. How's everybody doing?
Great.
Yes. I'm happy to hear that. Unfortunately, I am not doing terribly well. I'm a little sad, and I'm going through a bit of a midlife crisis. So what I'm going to do today is I am going to try to give the talk that I promised the organizers that I would give, but I'm going to give it in a context where I am having severe doubts about the work that I've been doing for the last 20 years or so and where the field is going. And I'm going to try to get some help from you to figure out whether I should be worried or not. Now, to set the stage for this, to set the context, I should point out that I should be extremely happy about the way the world is going. I've been arguing about bringing human beings into machine learning, and particularly reinforcement learning, for 20-odd years or so. Here, 2018, AAAI, we find that we have an entire track on human-in-the-loop AI. That's great. The president gave a wonderful talk about human-in-the-loop AI. So it seems like everything's going the way I would want it to go. But I made a mistake, and on Saturday, I went to the debate. Did other people go to the debate? It was a great time. Tom Dietrich got up, and he made what I thought was a pretty compelling argument that really everything should just be deep neural networks and convolutional nets, and everything else, nothing else matters. With enough data and blockchain, you can do anything that you want to do, right? And I thought, well, I don't think that's true, although, again, he made a pretty good argument, had a nice red tie on, he was very authoritative. But I thought it's worthwhile thinking whether there's any truth to the argument that he was making and to reflect on my own work before I gave a talk here. And I did that, and I sort of came to the conclusion that I'm unmoored. So I want to talk a little bit about that and try to kind of have almost a debate with myself like we had on Saturday about what interactive machine learning is and whether we're actually making any progress on it. So here's my talk. Now, before I do that, I feel like for any given talk that you have to set the stage. You have to give notation, you have to agree on terms and definitions. So I'm going to spend just a couple of minutes trying to do that before I get to the meat of the matter. So, interactive machine learning. My talk is supposed to be interactive machine learning. How do you learn from humans? Let me define what I mean by that, because I mean something specific by it, and this is what I mean. I mean, well, you take the normal machine learning problem, you've got data, you've got some magic black box, a model comes out, you use that model to do prediction control or whatever you want to, and interactive machine learning is basically the same thing, except somehow you put humans in the loop. Now, what's the point of having humans in the loop? Well, they provide information. They make the learning problem hopefully simpler. They provide labels, they influence the data, they identify important features, and maybe, depending upon your take on what human-in-the-loop machine learning is, they also help to interpret the learned model. In order to make that work, it turns out, and this is the thing where I'm getting a little lost, you have to model and predict human behavior. You have to actually understand what human beings are doing and understand whether they can give you the stuff that they want to give you. Now, the particular sub-problem of interactive machine learning that I care about is in reinforcement learning. I take it that most people in this audience are familiar with reinforcement learning, so I'll just go through it very quickly to give you some idea for those of you who are new to it. Reinforcement learning works. It's great. Everyone should do it. It solved all kinds of cool problems. And the formalism for it is just a slight change from the normal data in, model out that we do with supervised learning and other forms of machine learning. In particular, you assume you have some agent in the world. The agent lives in this world, this environment. It can take actions in this world. The actions that it takes affects the environment, the state that it's in. It gets some signal from the environment telling whether it's doing well or not. It takes that information in, it makes another decision, and so on and so forth. Typically, we model this sort of sequential decision-making problem with the Markov decision process, a Markov decision problem. It's a tuple. It's got states, it's got actions, it has a transition model, which describes sort of the physics of the world and this notion of reward. And your goal is to find a policy which tells you what to do in any possible state. What action should I take? And the optimal policy is the one that maximizes long-term expected reward. Now, like all machine learning problems, this is a difficult problem, and it's difficult because there's all these different pieces to it. You can have a lot of states, you can have a lot of actions, you can have a very unfriendly transition model, you can have very sparse rewards. There's all kinds of things that make the problem difficult and complex. But people have been thinking about this for many, many years. And so there's a whole ton of techniques, some of which were invented by people in this room, to deal with the problem of solving reinforcement learning problem even in difficult spaces. For the purposes of this discussion, let's suggest that they're mostly divided into three groups. There's the set of methods that worry about generalization, so we don't just have tables, so that we can actually expand for large state spaces. There's the set that try to tackle explicitly the notion of exploration. How do you search through this space in order to find an optimal policy? And then a set that are really about representation, which support both of those things. And again, they sort of cluster into a whole host of interesting algorithms. Now, what interactive machine learning and interactive reinforcement learning brings to the table is human interaction. That somehow, rather than thinking about just generalization, exploration, and representation directly, we should think about what happens if we can bring human beings in the mix. Why would we do this? Why would we bother to bring humans into the mix? Well, it's pretty straightforward. It turns out the problems that we care about are really, really, really hard. Some of these problems are so hard that because they're trajectories through space, they're hyper-exponential. They're so hard that if we had every atom in the universe printing out all possible trajectories at 1,000 a second, you still couldn't print them all out before the heat death of the universe. And so it's a very big space to search, and we need some kind of help, some kind of domain knowledge to get through. And you can sort of see this if you imagine that not only are there tons and tons of these possible trajectories from one space to another, but you have to search every single one of them to be sure that you're optimal. So how would you address this? Well, we're machine learning people. You address it by saying we just get lots and lots and lots of data, and sure, why not, right? Google's generated more data than all of human history in just the last 5 minutes. So is Facebook. Everything's fine. We'll just get more and more data, and we'll use that to solve our problems. But there's another way to think about it, which is, I think, somewhat more satisfying, which is that what we really care about is not having lots and lots and lots and lots and lots and lots of data. What we actually care about is having a small amount of data that's very good. If we get the right kind of data, we don't need billions and billions and billions of examples. We don't need every picture of a cat on the web. We just need one or two key things, and then from there, we'll be able to solve the problem very efficiently, get exponential speed up, and everybody wins. So how does that help us with human beings and reinforcement learning? Well, it's the same problem that we had before. We use XKCD to come in and help us. And they give us feedback on different parts of the learning problem. They tell us about the reward. They give us the proper reward. They give us a better representation for state, or they give us a better representation of actions. And between that, we'll have an easier learning problem. Now, this is the important part. This is where I start losing myself here. What is the fundamental goal? The goal, remember, is to leverage human beings in order to get good data so that we can solve the problem efficiently. So we want to take all the strengths of human beings, including people who are not expert in machine learning or expert in AI and the things that we do, and help us to solve these problems, which, by the way, often we are not expert in. We understand the algorithms and the tools, but we don't necessarily understand the domains. How can we get information from the domain experts in order to solve these problems? But of course, there are challenges. And those challenges revolve around a bunch of things, the usual things that we think about in machine learning and AI. There's a huge gap between the models that human beings have about what agents are doing and the representations that they're using. Raoul talked about this at some length during his presidential address. We have to actually build interaction. We have to come up with ways to understand how agents are performing and what human beings think are going on, because we're actually dealing with human beings. And humans don't always give us exactly what we want. They're sometimes noisy and suboptimal, and they're definitely non-stationary. So people have been putting tons of effort into this for at least the last couple of decades, and we end up with a ton of methods that roughly fall into a couple of camps: learning by demonstration, learning from critique, certain variations of active learning, and a lot of new work on using stories, natural language, and other ways of doing interaction to get information from humans. And that's great, but remember the point. The point is we want to get good data. If we can't get good data, then the whole exercise fails. So let me give you 2 quick examples, and then we can get to the issue that I'm having, and you can help me with this. So one example, or one type of thing I just mentioned, is learning from demonstration. The idea there is really simple. Without loss of generality, assume that the entire universe is a 5x5 discrete grid. You are starting in one part in the world, you're trying to get to some other part in the world, you don't know how to get there, somebody tells you, here's a way to get from S to G, here's a way to get from one point to the other, and then your goal is to use that information to build some kind of model over possible trajectories, make exploration easier, and then come up with the optimal policy without having to search through the entire space. It has some limitations and some issues. If you don't get good trajectories, if you don't get enough trajectories, you have problems. This is some recent work out of my lab that tries to deal with that, and it basically just tries to expand out of the space from where you're starting. By the way, for the grad students in the office, in the room, I should say that whenever you give a talk like this, you should always have at least one slide with the complicated equation that you don't explain, so people know that you're smart. I have 3 of them I'm not going to explain, so you know I'm really, really smart. The main issue here is that there's... Oh, that's fine. That's perfectly fine. I don't actually understand what they say. The main thing that's going on here is that by throwing a whole bunch of math and some gradients and some other stuff, and there's distributions and so on, we come up with a way of understanding the state space based upon what we're given. But the trick is, the whole point of this exercise is that we're not going to get the data that we need in order to solve the problem, and we have to build relatively complicated mathematical abstractions around it in order to learn something. Right? I hope you're beginning to see the problem that I'm having. One more example. Oh, it works. There's a graph, it works, it does really, really well. It does much better than not using those kinds of techniques, much better than supervised learning. So here's another quick example along this line. It's about critique, and particularly critique of policy. This is what people do. You have a normal, boring, Bayesian Q-learning, reinforcement learning agent going through the space. It takes it forever to figure out how to do exploration and to learn what's actually going on in the world. So you ask a human being to critique what it's doing. It says, oh, this was a good action, this was a bad action. It turns out that you can actually treat what it's giving you as a probability distribution on its own. And now that you have 2 probability distributions, you can combine them in sort of the straightforward way. You just sort of multiply them together, and then you have a true probability distribution over optimal actions under some assumptions about whether human beings actually know what they're talking about. And it turns out that if human beings know what they're talking about, you do incredibly well. You also do incredibly well if it's the case that human beings tell you what to do at every single place. And as they are more likely to be wrong, and as they are less likely to give you feedback, the problem becomes increasingly more difficult. This is a part of a long line of work. Pass will talk about it a little bit later. Peter Stone's lab has done a bunch of work in this space on action biasing. There's a lot of work out there represented in this room on this. And almost all of these algorithms have a bunch of things in common. The big one for me is they assume that people are wrong, and they have to throw in parameters and algorithms and tricks to deal with the fact that people aren't actually going to give you the answer that you want. So that gets us back to where we were. Can we get good data from humans? Remember, the goal is to leverage what humans know and to do a much better job than you would otherwise. But I sort of undersold the challenges. It is true that people are noisy and suboptimal, but it's actually much worse than that. It turns out people are dumb. They don't know what they're doing. They don't know why they're doing it. They're not going to give us the data that we need. And sort of the whole enterprise is a farce. I'll be 50 years old. Everything that I've ever done has been a waste of time. I feel pretty bad about this. So this is where I am right now. Worse. What's actually worse is that I know that somewhere out in the world, Jan LeCun is laughing at me. And he's going convolutional nets, and he's just laughing and laughing and laughing. This is a guy, so 20 years ago, I got an argument with him about the best place to get duck in Toulouse, and I swear he built an entire research enterprise just to ruin my life. It's a lot of good work. There's a lot of interesting things there. But this is an argument that is difficult, I think, to ignore. So here's the problem that I have. The problem that I have is that I am no longer convinced, after looking over my own work and looking over the field, that we actually can do what we are setting out to do, which is to take information from people and do a much better job of learning, when instead we should just be getting tons and tons of data from Google, Facebook, and whatever your other favorite company is. And that is actually going to solve all of our problems. And so I'm worried that rather than giving the talk that I said I was going to give, I'm actually going to end up giving this talk. So here's what I need. I need some help from the audience. I need help to think through whether I'm right or I'm wrong. I need to have a debate. I need to understand what it is that's actually going on when we are thinking about using human beings and leveraging them in this human-in-the-loop AI, human-in-the-loop machine learning, and whether the exercise is useful or not. So, who in the audience is willing to help me? Anyone willing to come up and debate me? Anyone? I see a couple of hands. You, young gentleman in the front, please come up and help me. Microphone live? You can use the mic.
What exactly is it that you need me to do?
Oh, well, first off, you should introduce yourself to the audience. Is this your first time at AAAI?
My name is Michael Littman. I have been to AAAI before. I was program co-chair actually a couple years ago.
I didn't come to that AAAI. So we've never met.
We've done several classes together actually. We've written papers together. You text me all the time.
I think that was somebody else. This is the online machine learning class?
Yeah.
I never met the person. I just saw their hands and I heard their voices.
No. That's because we were on Google Hangouts together.
That was just voices. It's a pleasure to meet you. All right. Okay. So I appreciate you volunteering to help me sort of think this through.
Okay. So wait. So you want me to give your talk? I don't understand what you want me to do.
I thought I set it up pretty clearly, right?
Oh, you're having a crisis of confidence.
I'm having confidence. I'm having a crisis of, let's say,
confidence.
faith. I need to convince myself. I need to understand what it is we're actually trying to do here.
Okay.
Because fundamentally, I think I've come to the conclusion that there isn't a point and that people are just not smart enough to help us with this problem.
I see. All right. So I think I can help with that.
Okay.
So you ask, what's the point? I'm going to say there is a point.
Okay.
No one can see that I'm saying that. No, that's not what I said. That's what I said. There's a point. Good. All right. You good?
I'm good.
We're good.
What's the point?
The point of interactive machine. All right. So your claim is that people are dumb, but I think I have a counter to that. People are smart.
And my counter to that is the one that I started out with, which is people are dumb.
I see. So I don't feel like we're really getting very far. So maybe we should get into some concrete examples. So let me see if I can present some information that will help you understand why it is that this should work, and in fact, it necessarily has to work. So the main reason that I think that interactive machine learning is absolutely necessary is because at the end of the day, people are the final arbiters of what the correct answer is, right? So we have to trust people to have the right answer, because otherwise, well, the machine will do something, and then if it's not what people want it to do, then it's sort of de facto wrong. So we have to believe people because people decide what's right, and also, for what it's worth, people know what's best for themselves.
So your argument, if I understand it correctly, is that people are useful arbiters of what a task is because they know what's best for themselves. Okay, allow me to retort.
Okay, all right. That's a cheap shot. There were extenuating circumstances, and this, we shouldn't take this as an example of what people are or are not capable of. So let's bring this back maybe to a more narrow kind of setup and talk about some particular problems in interaction, human-machine interaction, where I can prove to you that people are being undersold, and they can do more, and they do enough.
Okay.
Right. So let me start off with an example just to make it concrete. So this is now not a machine learning example exactly, but it is a human-computer interaction problem, and it's one that I worked on. So I'll give an example from my work, and then you'll have to believe me because I'm the expert because it's my work. All right. So been doing some work on trigger action programming in the Internet of Things. So the problem here is we have people who live in a house and they've got a lot of devices, and they want to be able to tell those devices what they want the devices to do. So we're going to use an end-user programming idea, trigger action programming. This is sort of popularized on the website, if this, then that. And they say that what will allow people to do is create little rules that say, if this is true, then make that happen.
Okay.
And what they did in the website, the way that they designed the website, is they only allow exactly that, if this, then that, not if this and this other thing, then that. And so we set out to show that, in fact, people could do more than just if this and that. They could do if this and this, then that.
If this,
It's a huge expansion over the previous work. And in fact, what we found is it is true. We gave people an interface, and we let them build recipes. We told them what exactly we wanted the recipe to do, what the little program to do, and they could very easily, in almost all the cases, they were able to construct rules that did what we expected. They were able to use conjunctions to effectively convey their intent to the machine.
Okay, so I don't think that's true, and here's why I don't think it's true. That's 2014, right?
Sure.
But something happened in 2015. Somebody else wrote a paper, and that paper is all about whether people actually understand conjunctions. And it turns out they don't. It turns out people do not know what they mean. You give them this language to explain what it is they're trying to accomplish. They think they know what's happening, and they do not agree with one another, and they're wrong. There's a bunch of examples up there. I'll pick on two of them. So Q3, if the doorbell rings and the time is 3 p.m., then unlock the front door in 10 seconds, and you ask people, you're expecting visitors in your house at 3 p.m., if you wanted to let them in automatically, would you use this rule? And if so, when do you expect the door would unlock? And a third of people say, yes, it'll work, and I'll use the rule, and it'll lock at exactly 3 p.m. Another third say, yeah, I'll use the rule, and it'll unlock between 3 p.m. and 3:01 p.m. And another third says, no, that doesn't work. It doesn't make, I don't understand how they got to that conclusion, but they said, no, it's not going to work. So even with something that seems relatively simple, it turns out the people cannot explain what it is they want, and even insofar as they can, they all disagree with one another. So given those kind of odds, it's not clear to me that you've actually learned anything or that you can learn anything from people. In fact, I'll point out with the last question, I really like this one. If the time is between 7 and 10 a.m. and the outside temperature is below 40 degrees, say in Providence, then I want you to brew a cup of coffee. So the question is, what's going to happen? Will the coffee brew if it's cold overnight? 2/3 of people say yes, it will at 7 a.m., and another third say, yeah, sometime between 7 and 10, presumably at every single moment in time between 7 and 10, it'll brew coffee. And by the way, I don't believe that those 2/3 actually agree. I think they're both saying yes for completely different reasons.
Yeah, that's fair. So, all right, so I think I see what I did wrong here. So I used an example from my research, which of course you wouldn't find particularly compelling because it's my research. So let me use an example from your research. Aha. All right, so in particular, let's look at the problem of problem decomposition. So when you're trying to learn new behavior, that's a really hard problem. And one of the ways that people do this is they, instead of thinking about the big problem all at once, they break it into smaller chunks. They can solve those chunks, put them together, and they can get a reasonably good answer very quickly. So as I understand it, you've worked on this problem.
I have.
And you look particularly at an example of training agents to play Pac-Man.
It's a fantastic game.
Sure. So in Pac-Man, you control a little agent, and it's going around, it's eating these pellets, and it can eat power pellets, which makes it really strong, and it can eat the monsters. But if it doesn't eat those, then the monsters can eat it. So it has to do all these things and balance all these different challenges all at the same time. And so what you did is you had people control an agent like that, but then you asked them this additional question of, what buttons could you add to the game to make it even easier to play? What are the kind of high-level things that you could have the game do that would actually help solve the problem more efficiently? And people, being super smart and insightful, actually were able to do this and come up with various kinds of, I don't know, subtasks or efforts that they could specify that would actually make things better. And so they picked, for example, going to a pack dot, which makes a lot of sense, or going to the Energizer pill, or eating one of the ghosts. And these are all subtasks that are actually very well modeled by the way that we think about things in reinforcement learning as, for example, options. They all have kind of a, this is when you want to do this is how you know when you're done, this is how you should behave while you're doing it. And it actually maps really well onto the way that we're already in the field thinking about these things. But they also had a really interesting insight, which is that you could ask people, people could ask the machine to satisfy an additional constraint. So, for example, avoiding ghosts, like go to the power pellet while avoiding ghosts, which doesn't really fit that nicely in the options framework, but it works really well as an additional constraint added to the planning process. And so, with just these 4 extra buttons, your team was able to construct a learner that could learn much more effectively than not having that kind of feedback. The feedback that people were providing was relevant, and it was useful, and it was powerful, and it was super insightful in that it was doing things that the reinforcement learning researchers hadn't even really considered in terms of its importance. So you can't disagree with yourself.
Okay, you're right, but, and I agree, that's great work. It is fantastic, and in 10 years I won an award for it. But you've only told half the story, right? So yes, it came up with constraints, people gave us an insight we didn't have, things sort of moved forward. I grant you that. But there's another example you should think about in the same space. So instead of Pac-Man, imagine, again, without loss of generality, we're living in a radiation world. So it's the same as Pac-Man in almost every way. You got north, you got south, you got east, you got west. It looks like the same problem. You have sparse rewards. The goal here is for a robot, that's the little robot in the bottom left-hand corner, to save what's apparently a zombie from a reactor and to safely get them away. So it's a normal search and rescue kind of thing. Now, what's interesting about this problem is that there are little pellets of radiation lying around, and it messes with the robot's navigation system. So if you run over the radiation, the robot explodes. If you get too near to the radiation, it messes up navigation and you start behaving in really unpredictable ways. So you kind of need to avoid the radiation. And it turns out that if you ask people to do this problem in the same way you ask them to do Pac-Man, you end up with something that on its face seems pretty cool. It learns that the thing you should be doing is going to the nearest human, very option-y, but you also need to avoid the radiation, which is in fact very constrainty. It's very good. And you're very happy about it. And you run, and you do really well, and you get very pretty graphs, and you get published, and everybody's happy. Except, it turns out that what people tell you, you cannot take literally. In fact, if you take the set of constraints and options, and you do all the same learning that you did before, which worked really well, you fail in any case other than the most straightforward one. And in particular, in this case, using those simple techniques, you end up with a problem where the robot saves one of the humans, but decides it can't save the other one. Although, in fact, the optimal thing to do here, very clearly optimal thing to do here when you set up the problem, is to try to save the second human, and the vast majority of the time you will, even with the uncertainty, because you can avoid running over the radiation. But the system never learns to do that because it believes what the human being told it. You can get around this problem only by ignoring what people tell you.
All right, so I see how this is going so far. So I make a proposal, which I think is a really good point, and then you come back and rebut it with the idea that if you literally take the feedback that people give you seriously, then you end up with systems that are not as good as really we would like them to be. Is that sort of where we are at the moment?
That's where I am.
All right, so I think to debug the format that we're in, I think what I need to do is have you go first. And then I can rebut you. That's really the problem. It's nothing but that. So let's look at a particular example that I know you thought about on learning behavior, or having an agent learn behavior given human evaluative feedback. So a person's giving reward and punishment, and the agent is learning from that reward and punishment how the person wants them to behave in the world.
Okay.
So why don't you tell us about how awesome this is?
Okay, so I know a lot about this. I've been working on this problem for a very, very long time. So I have a bunch of work. Here's my first observation. I appreciate your efforts at trying to turn it around on me, but I'm going to start out by saying that, in fact, you're wrong. And that it turns out that for all the standard RL problems that we use, the normal ways that we get feedback to agents, rewards and such, people don't actually deal with the world this way. So in particular, here's 3 cases. So I'll pick one from my good friend Peter Stone about feedback that you get on actions. Turns out in this work, you have to take gamma and you basically have to crank it all the way down to 0, which basically means you have to ignore what people give you.
What's
at least
gamma?
It's the little
It's that
symbol.
letter.
Yeah.
Yeah, no, I know. I know that, but what does it represent in this example?
The thing, gamma. You know, with the equation. What does it start with a B?
Bellman?
That one, right. So the thing that's going on here, though, and that's interesting because it sort of supports the idea that human beings can't be trusted, but it's actually more subtle and more painful than that. So if you go back to work in 2014, you go back to the 2000s when people first doing this, you have lots of other problems about actually interpreting what human beings mean by what they do. So in particular, a lot of times what happens is people don't tell you anything, right? And you have to deal with that don't tell me anything. And the natural thing to do, and what people even sometimes think they're doing, is they're telling you my reward is 0. But in fact, the reward is not 0. The reward is just, I'm not telling you anything. And all of the normal techniques that we have break under those assumptions. In fact, you see this even going back to the cobot work that Peter mentioned from a decade or so ago, that people stop giving you reward. In fact, here's what actually happens. You ask people to give you feedback about the world and to tell you whether an agent is doing well or not, and it comes back and they say, okay, and they say, yes, you're doing well, no, you're doing poorly, and so on and so forth, and then they just stop telling you anything because you've learned, right? And then they will only give you negative feedback when you screw up. But that breaks all of our models, right? Because at the end of the day, you're basically teaching the agent that it can't do anything right. The analogy that I like to use in my head is, you know, when you're young, you learn how to ride a bicycle. You learned how to ride a bicycle when you were young?
Sure.
Sure. So when you were young, you learned how to ride a bicycle, and the people gave you lots and lots of positive feedback. They said, oh, you're so wonderful and beautiful, and you're so cute, and so on and so forth. You get on a bike now, nobody's going to tell you anything, right? Right? Is that not your experience?
This is why I don't ride bikes anymore.
So we ask people to give you feedback. They don't give you feedback. They don't. And what they do is they tell you they're giving you what you asked for, but they're not actually giving you what you asked for. And you can see this in lots of examples. This is one of my favorite ones from your work, Michael. So here's the setup. You've got a little robot dog. It's very cute. You want to teach the robot dog to walk along the path and get to a door. And you want this robot dog to avoid stepping on all the pretty little flowers. So what do? Well, it's what you think you would do. You give it positive reward as it moves along the path towards the door. This makes sense, yes? And then the moment that it wanders into what's a very interesting looking garden, you give it some negative reward so that it won't do that. And that's fine. And then it goes back onto the path, and then you give it positive reward. And these people do this. And what happens as a result? What happens as a result of this is you end up with positive cycles. So what does the actual agent learn to do? The agent learns that the right thing to do is to step in the flowers so that it can get more positive reward by getting out of the flowers. Apparently you've studied my 10-year-old son, so you know how this works. Anyone who's raised kids knows this is how it works. So it gets the positive reward, and then it gets a little bit of negative reward for doing something wrong, but then when it finally does something right, yay, it gets more positive reward. And it never actually goes to the door. And why doesn't it go to the door? Because once you go to the door, all the positive reward stops. Right? Now, that's fine, you might say. Okay, you know, blah, 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 Andrew Ng, something about positive cycles, that's easy. But it turns out it's even worse than you think it is. When you give people feedback, when you give them an interface which allows them to see what they're doing, do you know what they do? They double down. They go, oh, it keeps going into the flowers and going back out in order to get more positive reward. So the best thing I should do there is give it more positive reward. And you just get into this infinite cycle, and the vast majority of people do this. And so therefore, you lose.
You have fallen into my trap.
I don't believe
So it
it.
was a good idea to have you go first, because now I can rebut you. And so here's my attempt at rebutting you. So first of all, I knew all that, because partly I wrote some of those papers, but mostly because it's sort of what you'd expect, that people, when they're giving feedback, are actually giving feedback that is critiquing the believed behavior that the agent has. So people think the agent is going to behave a particular way. If it behaves better than that, they give positive. If it behaves worse than that, they give negative. And so we showed this in a really simple little study, a little simplification of the flower bed example, where we had the agent behave very well, and then we gave a situation where the agent behaved sort of, you know, in the middle, and asked people to give feedback, and they would give negative feedback. You know, it was doing well, and then it was sort of doing sort of meh, and so they gave it negative feedback. But if we showed other people it doing really poorly and then doing meh, they would give it positive feedback because they were saying, yes, yes, you're going in the right direction relative to where I thought you were. And so what this is suggesting is that the feedback isn't really rewards to be optimized. It's actually a gradient signal. It's actually feedback or critique on the, now I'm doing gratuitous equations like you did before. But I'm not as smart as you, so I'll actually explain the equation. So this is the equation for doing gradient updates on policies in reinforcement learning. And there's a component of this which is exactly this advantage information, this how much better is the agent doing now than it was with the policy that it had been executing. And if you update the parameters of the policy with respect to that gradient, it will consistently move in a positive direction and improve. And so what this suggested to us is that if we take the human feedback, instead of plugging it into the reward part of the Bellman equation, we'll plug it into the advantage part, the critique part of the Bellman equation, and then we get an algorithm that's actually provably convergent. And in fact, when we try to train robots using this algorithm, the robots can do very sophisticated and interesting things from just this, this sort of feedback that we're giving it. And it does exactly what you'd expect from your earlier work. It's expecting people to wean their feedback away, because as the agent's behavior kind of becomes consistent and good, then there's no particular change from expected. It's doing exactly what's expected, which is zero feedback, which is what people actually do. So this is what people were doing all along. We just were kind of interpreting it the wrong way. So,
Go back a slide.
Go back a slide.
So you're claiming that this particular model of dealing with the feedback from people is supporting a bunch of stuff that I've said before. Diminishing returns, you talked about that. Differential feedback. What's differential feedback?
If it does way better, then you give it more reward. If it does slightly better, you give it a little bit of reward.
So way back when, there was a bunch of work that was being done on managing multiple sources of reward, right? And the model there was that people, if you treat all these multiple sources of reward as their own independent thing, and you brought a new thing, a new source of reward in, you needed to understand how that new source of reward changed with respect to everything else that was going on. Okay, so let me see if I can, so let me see. So imagine there are two people in the world, right? Let's call them A and B. No, let's say there are two actions in the world, A and B. I like that better. So there's two actions in the world, A and B. And I come into the room and I like A better than I like B. So what's a reasonable thing for me to do? Whenever the agent does action A, I should reward A. And whenever the agent does action B, I should punish it. That makes sense, right? And then you come in the room and you like A and B the same, right? So when you watch me, what's a reasonable thing to do? So one option would be to reward. You see me giving a lot of A's and not a lot of B's, so you want to drive it back into balance. So then you should punish the A's and reward the B's to bring them back. Okay, that makes sense. But then when I leave the room, what does the agent know about you?
It's going to think I only like B.
But that's not true.
Yeah, I like the balance.
So, okay, so then the argument here is that the information that you're giving to the agent is relative to the information that I was giving to the agent and what you thought was going on.
Yeah, the environment as a whole, sure.
Okay. Let's talk about policy shaping.
So this is back to the example that you had before. So maybe you want to revisit this in light of all you've learned on this journey?
Yes, let's do that.
Yeah.
Okay. So if I look at policy shaping and I think about it, what's going on here is that we ask people for rewards. Work with me on this. We asked people for rewards. But what they actually gave us was policy advice. They said, this is good, this is bad. They didn't say +1. They didn't say -1. They didn't say 10. They didn't say 17. They gave us something different from what we asked for. But understanding what they asked for allowed us to build a more efficient algorithm that still worked. So I'm not even clear, so it's in many ways a very actor-critic way of thinking about the world. So I guess I buy that argument. So in the end, people are stupid.
I don't think you've ever agreed with me before.
No, you're agreeing with me. What actually happened here is that you came around to my way of thinking, which is that people do not do the things that we need them to do, but we can still take advantage of what they do. And we can actually get significantly better performance than we would otherwise.
Is that what those graphs are showing?
That's exactly what those graphs are showing.
Nice. So
if you were way up here and you could read the graphs, you would see.
Judy can't read the graph. It's too far away. So, okay, so then maybe I've done my job here, and you're ready to actually decide the talk that you should have given all along. Not the what's the point talk, but the how to learn from humans talk that you wanted to do from the beginning. That's
Close. I think I'd change it a little. Yeah, I think that's a little bit closer.
All right, but let's not focus on the fact that people don't know what they're doing. Let's focus on the algorithmic side of it.
That's close, but we need to be honest.
All right.
Okay. I think that's better. I think that's about right.
So, okay, so that you think this is sort of where we've converged to. But my concern is that this is still kind of Frankenstein-y. It's got all these different pieces on it. We should come up with a sort of one clear way of thinking about how you should be thinking about this issue. So maybe let's go back to what we've learned.
Okay, so let's pop up a level. So I think you're right. So I think going through the actor-critic thing sort of helped me to clarify my thoughts a little bit on this. I'm going to claim there are two things that we got out of this. One of which I'm going to say is obvious, and you have to agree with me because I just said it was obvious. And then the other I don't think is so obvious. So, and maybe it's more of a reflection of me. So here's the obvious thing. It's not about smart versus dumb, right? It's not that people are smart or people are dumb. I mean, they're dumb. We know that. It's not that people are smart or that people are dumb. It's that they're different, right? When we ask them for rewards, they might give us policy advice. When we ask them to give us feedback about how the agent is doing, they might do something entirely different, but which makes sense. This sort of differential award you're talking about, that makes sense. Actually, if I think about all the examples we've given, every single one of them has this flavor, right? Which is the machine learning researchers say, this is what my algorithm is, this is what I need. We ask the human being to give it to us, and they give us something else. Even going to the very beginning with the conjunctions, we had a language which in theory had a meaning. The human beings understand English, and they had a completely different meaning, and there was mismatch between them, but that was basically it. So there's signal there. The secret is understanding what the signal is. So this brings me to what I think actually matters, at least matters to me, and I think I'm going to have to start rethinking the kind of work that I do. I'm going to claim that a lot of us, and I won't speak for anyone else in the room, I'll just speak for myself, think of ourselves as computational statisticians. We think of ourselves as building these algorithms and building equations and finding, Kale divergence between distributions and things like that. And we actually outsource our understanding of human beings. We ask the cognitive scientists, we ask the people who do HCI to go off and run our user studies for us so we don't have to do IRB, and we never actually, which, has its ups, its positive sides, and we try to work on the numbers. But the truth is, we can't actually really take advantage of what human beings are willing to give us unless we make it a part of our everyday job to understand what people are. We need to do the cognitive science. We need to do the psychology. We need to do or at least have our students fill out IRB. We need to do these kinds of things in order to make it work. So in fact, it's not about humans in the loop. It's that humans are the loop. And they're first-class citizens in the mathematical problem that we're trying to solve. You buy that?
I do. I think we've learned a lot.
Together.
So, all right. So here's where I think we are. I think my job here is done because you seem to have had an epiphany, and so you can just kind of move on with your epiphany. But we should at least say what the talk should have been from the beginning.
Sure. That's not quite right. I like that.
All right. So you can now give that talk.
Thank you, Michael. So I like that talk. I think that's the talk I should have given, but we don't have any more time because the program said 9 and the other program said 8:50, so we started a little late, so I've only got 5 minutes for questions. So instead of giving that talk, I'm going to suggest slides. I'm going to suggest that you go to the other talks that are happening today on human in the loop AI. There's a couple that are happening this morning and a couple that are happening this afternoon. Those are happening in the room right next door, and you have a bunch of people doing a lot of interesting work in this, and I'm completely sure that they will do a better job than I did of understanding what it is they're trying to accomplish with that work. So before I bring the talk to the end and take any questions, I would like to acknowledge all the people whose work was behind it from my lab, including a bunch of faculty in aerospace as well as in computer science and in various departments, a bunch of research scientists and postdocs, and of course, a bunch of students. Do you have anyone you would like to acknowledge, Michael? Okay. And then there's other people. Who are these people? They're people. That's Dave Roberts. I had him on my slide. I knew him when he was young. That's fine. So with that, I think I will bring the talk to an end, and I'm happy to take any questions.
I'd be happy to start. So first off, thanks for the plug. I'll be speaking in just a few minutes, but I actually wanted to rebut the idea that deep learning is going to take over everything, which is
Please.
Somebody is curating that data, right? Some of these problems, images, okay, there's a lot of rich image data. We can just throw it at the model and see what happens. Once we start talking about more sort of reinforcement learning problems, curating that data actually becomes a lot harder if you want to learn a desired behavior. And so that's still a human in the loop, picking what the training examples are. I don't think we can get away from that.
No, I think you're right. It's true. I think, though, in a lot of the ways that we think about the problems, we pretend that the data comes, sort of sui generis from the universe, and we don't have to worry about that problem. But the people who are doing that typically are experts a lot of the time. And certainly in the work that we do that's going to develop the basic algorithms that eventually people in the real world are going to deploy, we typically curate the data ourselves, sometimes specifically in a way that sort of drives us towards a particular conclusion. I think it's a perfectly fine point. Yes?
So I think that maybe you're solving the wrong problem.
Okay.
Because you assume that you have a well-defined reinforcement learning problem, and maybe people can help you solve that problem. But once you have a well-defined problem, then maybe computational methods can solve it quite readily. But we all know that the hardest part in developing any application is actually formulating the problem in the first place. And I think tools that help people go from a general conception of what they want to do to a formalized reinforcement learning problem may be the place where the interesting research might lie.
So I'm going to agree and disagree with you. So the way I'm going to agree with you is I think that one of the things, and I think a lot of people have spent time thinking about this, is it's a kind of searching for your keys in the spot under the lamp sort of problem, where you decided that the MDP represents the problem that you care about. And so you build all of these algorithms, all of these techniques in order to solve the MDP as if the MDP were the problem. But as you're saying, the MDP is not the problem. The MDP is a programming language or representation that represents the problem or the task that you're trying to solve. And it's very easy, once you've come up with this formalism, to get stuck in the formalism and forget how you express the formalism in the first place. So I think that's absolutely right, and that, in fact, a lot of work we ought to be doing, even in reinforcement learning, is moving beyond the notion of the MDP as the object to start with, and instead move to think about it as the programming language that represents or specifies the problem. And it doesn't have to be written in the language of an MDP. It can be written in the language of psych. It can be written in the language of whatever your favorite tool is, or your favorite way of thinking about the world is, and then compile that, so to speak, to something that a reinforcement learning agent or the algorithms we have might be able to use, or a logic-based system might use, or that can be shoved into a convolutional neural net, or whatever it is you happen to be interested in. So I think you're right on that. I think the disagreement I have is, I'm not even sure it's a disagreement. I think the disagreement, insofar as I have one, is that we have to start from somewhere, and we have to get it to a place that we can do. And even if you think about the work that we talked about here, right, so much of it was starting in a place and then having human beings tell us that our formulation was wrong and giving them the tools to help us. But you had to start from a place and then do the interaction and the conversation necessary in order to move it to something you can solve. You can't start with them giving it to you because they don't understand the language of the machine any more than you understand the complicated domain that you're trying to represent.
Thank you.
Sure.
He was first.
Okay.
So sort of a follow-up on that, another alternative would be, instead of looking at reinforcement learning as the starting place and ask how can humans interact with reinforcement learning, to ask, how do humans teach other humans? And we do not usually give rewards, except when I was teaching my daughters to be toilet trained, and I would give them a M&M.
That did not
Day
work
to
for me.
day, that worked. Day to day, if I was depending on reinforcement learning, I don't know that I would have learned much from this presentation. I think it would be useful for us to take a step back and say, how do humans communicate with other humans in order to teach them new things? And that might lead us to a broader idea of how can humans help computers down the road.
How can I disagree with that? I think that's right. I don't think it's too different from the conversation that we just had. A lot of work that so I'll give you an example of a bunch of new work that's coming out that's not in my lab, but people that I know. There are a lot of people from the world of narrative and storytelling who are using what we understand about how humans tell story to build algorithms that can extract from story what it is that someone's actually trying to accomplish. Those are extremely difficult problems because when we have these conversations around story, there's these massive gaps that people don't have a problem dealing with. And when they do, they have a conversation about it in order to kind of get to where they're going. All conversations and negotiation in some sense, right? And so we should be focusing on that. Now, I think it's perfectly fine if, while in the process of doing that, you turn it into a reinforcement learning problem or you turn it into some other problem. But the important part is that if you're going to bother to engage with human beings, you have to actually meet them where they are and deal with them in the way that they want to teach others, including accepting the basic knowledge base that they have coming in, the assumptions they have about the way the world is working, and so on and so forth. So I completely agree with that. I also think that it's hard. It's extremely hard.
Research is hard, yeah.
Research is hard.
That's what we're here for. Thanks.
Fair enough. Yes.
So thank you for your talk. It was very enlightening. My main question, I guess, is have you thought, or do you have a few words about how this, how your feelings about this impact how we view humans as arbiters of what our good goals are? So in the sense of we're all building machines to have some end goal, and we have a context that we're designing those for, and how can we better make sure that we're actually reaching the goal that we want or that we as a community want, and not just sort of some slice of that, I guess.
Right. So you're now asking a pretty philosophical
Yes.
question, right?
Sorry.
No, there's no need to apologize. I think half the people in this room got into AI because of the philosophical questions that it raises, as opposed to the derivatives that you get to take. So I think it's a perfectly reasonable question to ask. I don't think I have a better answer than most of the people in the room would have, except to say that it's a part of having a conversation. I think right now, and in fact, I'll get on a soapbox for just a moment. The real answer to your question is we have to build those questions in from the beginning of the enterprise. So let's take a very simple, well, not simple, but let's just say a relevant example going on now, which is around ethics. So there's lots of conversations going on at this conference, going on around the community about ethics and AI. I think the one conclusion that I've drawn based on those conversations is that the ethics and AI question is not something you ask after the fact, it's something you have to ask at the very beginning, and you have to be ready to treat, thank you, and you have to be ready to treat it as an iterative process where you're constantly re-examining the question. If you have it, it's a pop book, and so it has its problems, but if you really want to see how badly this can go, I recommend Weapons of Math Destruction by Katie O'Neill. It is a perfect example of how you use data to get to a particular place and then you ignore the fact that you were answering a completely different question from the one that you thought you were asking, and you're hurting lots of people in the process. But if I thought that the last question was a hard one to answer, this one's very hard because you're asking me to fix people.
Well, I just wanted to hear your thoughts on it, so thank you so much.
Absolutely. Thank you for the question. So yes, and then it's gonna, I think it'll be time for people to run to the next talk.
Yeah, so thanks for the great talk. Building on the previous question about sort of how humans learn from each other, it seems like one of the things that you do in your really awesome classes, both of you, and you did in this talk, is sort of build, a shared representation, a shared sort of language. So you can, first you sort of establish like a way of communicating, right? So that I can understand you, and then, only then can you really communicate the goal. So do you think it might make more sense for sort of these models and human beings to try to develop more of a shared sort of way of representing things in the world? Maybe there's work on disentangled representations that seems like it's pushing towards some of that before you can integrate sort of this feedback about policies or goals.
Yeah, so and we do that now in our own work by, I mean, when I say we, I mean we do that in our own work by setting up the problem in a particular way and then trying to ask people to do it in the way that we are. And even in the very simple cases like the Pac-Man case, the radiation world case, the conjunction case, it turns out that there's a large gap there. This is what Raoul's talking about in part when he talks about the model gap. I'd also call it the representation gap. I think that it is important that a significant portion of the community spends its time thinking seriously about long-lived teamwork as a way of attacking that problem. And lots of people in this room have done that. Peter's done a bunch of work on this. I'm sure, I can't see anyone because the lights are in my eyes, but I'm sure I could point to 8 other people who've done work like that too. Just to give you a feel though, so yes, you should do that, but just to give you a feel of why that is difficult and why it's important that it be done. Here's a result that, you know, sort of from the world of organizational theory. If you take a set of people and try to get them to solve a problem, and then you separate them to go work on the problem and then come back together, typically what happens is when you separate them, they come back together and they've effectively invented a new language amongst themselves and they can't talk to one another. So the stark example of this that really hit home for me is you put people on 2 different sides of the room and they start talking about, you know, things that they should be doing to make the room more livable or something like that. It doesn't really matter. And one side of the room is staring at a clock and they will start talking about the room or the world in reference to the clock. The other side of the room isn't looking at the clock and looking at something else. When they get back together, it turns out these people don't even see the clock, even though it's literally in front of them, because they've constructed the shared representation amongst themselves that allows them to be efficient. And when you bring those 2 things together, because they don't have the same underlying basis, you can't even have the conversation in the first place to realize you're talking past one another. Anybody who's ever tried to do interdisciplinary work knows that it takes you 2 years just to agree on what probability means, right? And that is the part that's really hard. So I think that for a lot of the work that we do and for the question you're asking, you have to take that problem on directly.
Thanks.
Sure. Last question.
Thank you for a thought-provoking and hopeful talk. Going back to sort of what this debate between deep learning and logic, am I hearing correctly that when you say meeting humans where they are, is it part of your tacit assumption that we're always meeting machines where they are? So for example, are we always looking at, part of the promise of deep learning is autoencoders will evolve representation, right? They'll evolve constraints, they'll select examples, they'll create new features. What will that look like? Are we always meeting them where they are in terms of humans in the loop currently are providing context for those constraints? So
we're certainly not always meeting people where they are. I think the problem, and this is hardly my insight, I think lots of people have had this observation, is our habit as engineers, as computationalists, is to figure out the equation that we want and then demand that human beings come and give us the data that we need in order to do whatever computational process we need to solve whatever problem we're trying to solve. And what's interesting about these kinds of approaches is they take seriously the idea that you have to change your algorithms, you have to change your interfaces, you have to change your representations to meet people. People still have to move a little bit towards you. I mean, that's what negotiation is about. But I don't think the problem is people not coming. The problem is not people coming to machines. The problem is machines not coming to people, which is really a problem of the people doing the work, the engineers developing the system, of not trying to reach people where they are.
Are we currently trying to meet machines?
Some of us are. Some people are. Lots of people are. We're not doing enough of it. And it's not hard. It's not easy. It's very difficult and it's highly inefficient in many ways, especially if the answer is, I can just download 100 trillion terabytes of data.
Right.
It seems like a much easier problem to deal with.
Thank you.
All right, thank you. All right, thank you, everyone. Please enjoy the rest of your time.